Alright, this is corresponds to section 7.1 and 7.2 in your textbook. The unit is on exponents, exponential functions. This is exponential growth and decay. And so we're doing these applications, and we can model everything with the equation like this. This is the main equation you need to know for this unit. It's y equals ab to the x power. And if you understand what everything means in this equation, you'll be able to model anything. A is actually, in the problem that you're doing, is the initial value that you start with that will be increasing or decreasing. A is the initial value. B is what you are multiplying by that will determine whether it's growing or decaying. And so this is called the multiplication factor, because you keep multiplying by that number. That's the multiplication factor. And x is your exponent, and because exponents mean repeated multiplication, so that means the number of times, and I'll just say that informally, it's the number of times you do it. Number of times you do it. Whatever it is. And so sometimes you have to read the problem and make sense of it to know how many times to multiply by the multiplication factor. What I mean by do it is how many times do you multiply by this number. So usually the initial value is obvious. The hardest thing to come up with is the multiplication factor. So let's look at some examples for just b. So if I told you b was 1.20, what does that mean? Is that growth or decay? Growth. Good. Growth. So grows. And what percent are we growing by if b is 1.2? Grows 20%. So what if my multiplication factor b is 1.03? Then what do I, is that growth or decay? Growth by how much? Grows 3%. 0.03 stands for 3%. What if I do the 2? What's happening intuitively? If I keep multiplying an initial number by 2, what am I doing? I am doubling. If something doubles every time, you multiply by 2 every time. So it makes intuitive sense. If I multiply by 3 every time, I am tripling. Those are all examples of exponential growth. So when b is, notice when b is greater than 1, we have growth. And now let's do some decay examples. So in half-life, which is an application you're going to get to, all you do is multiply your initial value by a half, or 0.5. That's the same thing. So that cuts the initial value in half, and it's called half-life in your applications in science class. It's called the half-life. So you're going to be all the better for it that you've seen it here. If you want to, be careful, what would 0.60 do? Is that decreases by how much? Yeah, decreases 40%. It's not, okay, because the work that you would do ahead of time is you would do 1 minus 0.40, and that gives you that. So this, if your multiplication factor is 0.60, that decreases by 40%. What would it be if you wanted to decrease 25%? If you want a quarter of it every time, what would you do? What's the multiplication factor? Good, 0.75, because that's 1 minus 0.25. So these are all called decay. So exponential growth and decay is there. And now what do the graphs of these look like? Just so it's in your notes, and we can introduce one other new thing. So that's how you model with an equation, okay? And when you do these, the graph for growth will look something like, we're usually most interested in quadrant 1. It'll have some start value, and then it increases. But the graph does go in both directions, but usually we care about the start value and how much is it growing by. So the graph for decay usually looks like you start at some whatever value it is, and you decrease sharply and then level off, and that's what decay looks like. And so the reason I'm showing you these is because there's this very important thing. When you decay, even if you cut in half forever, will you ever hit, let's just think about decay. If you continually cut something in half forever, will you ever have nothing? Good, good. So you understand that intuitively. Good. So the class says no. So this x-axis right here in both of these examples, the x-axis is called the asymptote, and you never touch it. So this is the line of no touching. Line of no touching. And the word for the line of no touching is the asymptote. So you have to have that in your math vocabulary, because you'll see these all the time in different graphs. More complex graphs use asymptotes. And usually we see it as a dotted line, and the graph cannot touch it or cross it, because it will just never arrive. It'll get closer and closer, but it will never arrive. So those are asymptotes. And now one other thing I need to explain for these applications is, with money, there's different types of compounding interest. So this will be the last part of the notes. For compounding interest, I'm going to just do one example so that you know how to do these intuitively without memorizing a formula, and then that will be it. So for example, if I have $1,000, and that's my initial amount, and I want to, and my rate in this example is going to be always 5% is my bank rate. If, depending on how I compound this, I will end up with different amounts in a year. So depending on how I compound, I'll end up with different amounts. If I do it yearly, which is what you almost always see, then my $1,000 will become, it's very straightforward. What would you multiply by for your 5%? What's the multiplication factor? For 0.05, nice. So it'd be, technically it would be 1.05, right? So I'm going to write it as 1 plus 0.05 so you can see this. And you would only do it one time. That's the exponent. You would just multiply it by that one time. And so on your calculator, without your calculator, how much money are you making on $1,000 if you're making 5% interest? This would be good it's really good to know how to do these things in your head. Let's start with, this is what you would do. You would go, what if it's just $100? How much does 5% give you? $5. So what about $1,000 then? 50. So you made 50 bucks? So the answer would be 1,050, okay, in a year. So what that tells you is, in a year you invest your money at the bank that gives you 5% interest compounded yearly. That gives you 1,050. Now if I change this to quarterly, how many quarters are in a year? There are 4 quarters in a year. So you need to go like this. You don't get 5% 4 times a year. You get a fourth of 5%, but you compound it 4 times in the year. So that is what, so let's see what that would give you. If you type this in on your calculator, you need to make sure to use parentheses here, and then raise it to the 4th, hit enter, and then the last thing is to multiply by 1,000. This is order of operations, PEMDAS. Do what's in parentheses first, then raise it to this exponent, and then multiply by that. So I want you to tell me what you get, and now let's write out monthly. While we're doing that, let's write the formula for monthly. You would take $1,000, that's your initial. How many times monthly? What does monthly mean? How in a year? 12, good, 12 times. So you would take a 12th of 5%, but you would do it 12 times, and that'll give you something different. And finally, daily is the best, but I would be hard pressed to find a bank that's going to give you interest compounding daily. But if you find it, please email me. So that would be 0.05. How many times? 365. Raised to the 365 power, because you're going to do it 365 times. So I want to know what all these amounts give you, and then we're good. So,
What about leap year?
all right. Leap year would probably change the number of days. Is that right? What does a leap year do? I don't know. It's 366. Okay, so that would change things a little bit. Good. So what did you guys get for this? What do we get? So if we compound quarterly, you should get 1050, and you should get another 95 cents. And if you do monthly, you should get 1051.16. And if you do it daily, and notice this is all the same percentage rate, it's just compounded more frequently. It matters. It does make a difference, a little difference on that amount of money. Okay, so it slightly changes depending on how you compound it.